In this video, I will present our work EffiScene, efficient per pixel rigidity inference for unsupervised joint learning of optical flow, depth, camera pose, and motion segmentation. The goal of this work is to efficiently estimate the scene flow from any given image pairs in a sequence of video without ground truth. Different from 2D optical flow, scene flow describes the 3D motion of a dynamic scene by optical flow and the depth change, providing more essential geometric clues for many vision applications. To achieve this goal, we introduce a new scene flow structure named EffiScene and a novel rigidity from motion layer. Besides, two new losses are also designed for easy training. All these demonstrate that per pixel rigidity can be efficiently predicted by joint learning from different tasks. In existing scene flow methods, auxiliary instance segmentation network is adopted to separate an image into static and moving areas, so that the equal motion of background can be restricted. However, this independent structure will make the critical rigidity inference inefficient and hard to be optimized. Different from them, we are motivated by observation that the rigidity of the scene shares the same inherent geometrical structure with optic flow and depth. Hence, they are highly correlated and can be mutually beneficial. In the proposed EffiScene, we first estimate optical flow and the scene depth at the coarse level. The flow CNN takes two consecutive frames as inputs and outputs a two-channel optic flow, while the depth CNN uses stereo left-right view images at time t and generates a single-channel disparity map. Since optic flow and depth are obtained, camera pose can be computed by minimizing the reprojection error between the transformed coordinates and the projected 3D points. After that, we can easily get rigid flow from depth and camera pose. Next, we design a novel rigidity from motion layer to adaptively learn rigid optical boundary by explicitly modeling the correlation between various flows. The forward process includes 3 steps: correlation extraction, boundary learning, and outlier exclusion. The first step constructs a pixel-wise correlation map by this equation, in which Fc evaluates the per pixel similarity between flows, and N is the normalization operator. According to the central limit theorem, the distribution of correlation map in rigid region can be modeled as 2 Gaussian distributions with mean values 0 and 1. Based on this, we approximate the Gaussian mixture model by designing a fully connected network in the second step to automatically regress the optimal rigid boundary from histogram. Finally, in the last step, we generate a region map by excluding local motion outliers from the global motion. Alpha control the balance between hard and soft mask. Back to the EffiScene framework. Optic flow and rigid flow are fused to form the final flow, guided by the rigid map from RFM at the final level. By doing this, different modules in EffiScene can be closely coupled by RFM, and all components can be clearly interpreted from the geometrical view. Therefore, the efficient rigidity inference can be carried out via jointly considering the geometrical information from flow and depth. EffiScene can be trained with standard photometric loss. To avoid the trivial solution, we design a new boundary loss to encourage RFM to find out more inliers by restricting the area ratio between rigid and non-rigid regions. Furthermore, an uncover loss is also introduced to regularize the flow discontinuity at the image boundary. Extensive experiments conducted on Kitty benchmark showed that EffiScene could against state-of-the-art scene flow methods in all 4 subtasks: optical flow estimation, stereo depth prediction, visual odometry, and motion segmentation. In our future work, improving RFM in large occlusion and exploring long-term dependency will be the next goal. Thank you.